be talking about is Spark. And so this goes back to sort of almost to the beginning of the semester, where we talked quite a bit about MapReduce. And in fact, lab one, you implemented MapReduce. And really, what's one sort of informally, the Spark is basically the successor, to Hadoop. And Hadoop is the sort of open source version of MapReduce. So I think today, people typically will use Spark instead of Hadoop. And so it's really widely used. And it's widely used for data science computation. So people that have lots and lots of data, that need to run some computation over it, require a ton of machines. Spark is designed for that particular case. It is commercialized by a company called Databricks. Matej Zaharia, who's the author or the main author of this paper, his PhD thesis, started with a number of other people, this company Databricks, which commercializes Spark, but it also supports the Apache open source Spark version. This is a pretty popular open source project, or very popular open source project. It is one reason has sort of replaced the use of Hadoop is because it actually supports a wider range of applications than MapReduce can. And in particular, it's very good at these iterative. What happened there? Let me see something. Maybe external crashed. Hold on a second. Okay. Fortunately, I think we're in good shape. Okay, so it supports a wider range of applications, and in particular, it's good at these iterative applications. So applications where there are multiple rounds of MapReduce operations. So if you have an application that requires sort of one set of MapReduce followed by another set of MapReduce followed by another MapReduce computation, Spark is really good at it. And the reason it's so good at it is because basically it keeps the intermediate results in memory and has really good support, programming support for doing so. In some ways, the sort of if there's any connection at all between the previous paper and this paper, which there basically is not, but they're all both targeted to sort of in-memory computations. For data sets that basically fit in memory. In the previous paper, in the farm paper, it's all about the database fitting in memory. Here is the data set of the data science computation for the data science computation that you want to do. Of course, since 2012, when this paper was published, a lot of things have happened. Spark is not really tied to Scala, as is sort of described in this paper, but there are other language front ends, for example. But probably more importantly, the RDDs as defined in this paper are slightly deprecated and replaced by data frames. But data frames, the way to think about it, or at least the way I think about it, is basically a column is an RDD with explicit columns. And all the good ideas of RDDs are also true for data frames. And so from the rest of the lecture, I'm just going to talk about RDDs and think about them as equivalently to data frames. Any questions before I proceed? And then, quick other point, maybe this research is really quite successful. As you said, it's widely used. Also, Mate, received the ACM doctoral thesis award for his thesis that basically is all about Spark. So it's quite unusual, actually, for a doctoral thesis to have that kind of impact. Okay. So the way I want to talk about Spark is by just looking at some of the examples, because I think you get the best, you understand the programming model that is based on RDDs best by just, I think, looking at examples. And you get the best idea of like what actually an RDD is. And so let me pull up some of the examples that are in the paper, and then we'll walk through those. Let me pick this one. So let's start here. Very simple example. And so, the idea is that in this example is that, first of all, you can sort of use Spark interactively. You can sit at your startup Spark on your workstation or your laptop and start interacting with Spark. And the way you can type in commands like this. And so what does this command do? This basically creates an RDD, called, this is RDD, lines is an RDD, and it just represents an RDD that actually stored in HDFS. And the HDFS might have many partitions for this particular file. So for example, the first 1,000 or 1,000,000 records live on like partition 1, the next 1,000,000 live in partition 2, and the next 1,000,000 live in partition 3. And this RDD lines basically represents that set of partitions. When you run this line, or you type in this line and you hit return, basically nothing really happens. And so this is what the paper refers to as lazy computations. In fact, the computation is executed some point later, and we'll see in a second when. But at this particular point, the only thing that's actually happened is that there is a lines object that happens to be an RDD. And an RDD supports sort of a wide range of operations. We can actually look at a little bit at some of the operations that it supports. So it just has an RDD has an API, and it turns out that the methods on the API or the methods on an RDD fall into two classes. One are actions, and actions are really the operations that will actually cause computation to happen. And so all the lazily sort of build up computation really happens at the point that you run an action. So for example, when you run count or collect, then the Spark computation actually is executed. All the other API or methods are transformations, and they basically take one RDD and turn it into another RDD. It turns out that every RDD is actually read-only or immutable. So you can't modify an RDD. You can only basically generate new RDDs from an existing one. And so if we look at the second line, this basically creates a second RDD, the RDD errors, and that one is created by running a filter on the lines RDD. So the lines RDD is in a read-only, RDD is read-only. You can run this method to filter on it, which in this case basically filters out all the records that start with, or all the lines that start with the message error or the string error, and that represents a new RDD. And again, at this point, nothing actually is really being computed. It's just like a recipe, or it builds up like almost like a data flow, or what the paper calls a lineage graph of the computation. Also, when the computation actually starts running, it hasn't run yet, but when it will start running, these operations are pipelined. And with that, they mean that, so for example, in stage one, this computation of the lines, the stage one will read some set of records, from, for example, this first partition, and then do its processing on it, if there's anything, and then hand it off to stage two, which is stage two is basically, doing this filter. And so in stage 2, this filter will run and sort of grab out the lines that actually are that match, and basically produce with that a new RDD that just contains the lines strings that start with lines that start with the string error. And while this sort of second RDD or the second stage runs, the first stage grabs the next set of records from the file system, and then feeds them again to stage 2. And so as you go further and further, you have more and more stages in your pipeline or your lineage graph. All those stages are going to be running in sort of in parallel, and that's what I mean with like sort of pipelining the transformations. Okay, so here this line basically describes how to create the RDD error, the RDD errors RDD, and then this line basically says like tell Spark to basically keep a copy of this RDD in memory. So if subsequent computations run that do more stuff with errors, Spark will actually keep the original RDD actually in memory, so that it can be shared with later computations. So for example, if we wanted to reuse the error file, then that error file will be in memory. It doesn't have to be reconstructed from the files that are actually represented in HDFS, and allows you to run the second computation. And here, for example, one already, even in this simple example, you'll see there's sort of a big difference between this and MapReduce. Like in the MapReduce job, you run the computation, it ends, and then if you want to redo something with the data, you have to reread it in from the file system. And using the sort of persist method, Spark can avoid having to reread that data from the disk, and save a lot of time. Any questions so far?
So when the error file gets extracted from P1, let's say, and then there's another error file that gets extracted from P2. So my understanding is that these happen in parallel?
Yes. So you can think about it like, there's going to be many workers, like in the MapReduce, and the workers work on each partition. So basically, the scheduler will send a job, to each of the workers, and a job is or a task, pertains to a particular partition, and the workers start working on get one of these tasks and basically start running. So you get parallelism between the partitions, and you get parallelism between the stages in the pipeline.
I see. Thank you.
Sorry, yeah. Can you hear me? What's the difference between the lineage and the just the log of transactions that we've seen before? Like, is it just the granularity of the operations?
As we'll see, lineage, a log is strictly linear, right? And the examples that we've seen so far, the lineage is also linear, but we'll see later examples where we have forks, where one stage depends on multiple different RDDs, and that's just not representative in the log, right? There share some similarities in the sense that, like, you start in the beginning state, all the operations are deterministic, and then you will end up in some, and if you apply all those operations, you will end in some deterministic end state. So in that sense, there's some similarity, but I think they're quite different.
I also have a question. In this case, filter, it works by just applying filter on each partition, but sometimes, like, I see the transformations also contain join or sort.
Yeah. Let's talk about this a little bit. I will talk about sort and join in a second. Okay. They're clearly much more complicated.
So does persist is when we start computing?
No, nothing has been computed yet. It's still all description. So let's talk a little bit further. Let's look at actually something that actually generates a computation. So here are two commands that actually result in computation. So this command will result in computation because it contains count, which is an action, and this command will result in a computation. Collect is an action. And so And so you can, and so we look at looks like, and so the reason that they show two commands is because to demonstrate that basically you can reuse errors. And so if you look at this computation, then you can draw the lineage graph, right? So it starts with lines. There was a filter that we ran. Oops, sorry, let me write it slightly differently. There was a filter on lines that we just saw that produces errors. Or that's the description how to get errors. Then there's in this case, there's another filter. It's the filter on HDFS. And that basically produces another RDD. That RDD is not explicitly named here, but it does produce another RDD. So I'm just going to call it HDFS because it filters on HDFS. And then we see there's a map, and that produces yet another RDD. Again, this RDD doesn't really have a name here, but so it's anonymous. But I'm just going to give it a name. That's a time, because it basically splits the either line into 3 pieces and grabs the third piece out of that line, and that happens to be the time. And then there's a final, operation, and that's collect, which then actually counts up all the number of times that time actually appears, or the number of entries basically in the result of in the RDD produced in the time RDD. Okay, so this is actually at this point when the return, you hit return here in the user interface or in the interactive user interface. It is at that point basically Spark will collect a set of workers, split, send them the jobs, and basically inform the scheduler that a job needs to be executed, and the description of the task that needs to be executed is this lineage graph. And so we can sort of think a little bit about exactly how the execution happens. So let me draw a picture. And so the picture is as follows. We got this, what is called the driver. That's the user thing. It's where the program that the user types into. It starts off collecting a bunch of workers, a bunch of machines, almost the same way like as in MapReduce. And there's going to be in HDFS, there's this lines file that actually has partitions, P1, P2, whatever. Bloom, 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 bloom. And typically the number of partitions is larger than the number of workers. The number of partitions is larger than the number of workers. You go to get some load balance. If like one partition is small and the other one is big, so you don't want to have workers sitting around idle. And basically the scheduler, there's a scheduler that runs, basically the computation, and X has the information that has the lineage graph. And so workers basically check in, the driver actually sends them the code, the Spark program that we just constructed, and then the workers go basically to the scheduler and say, please, on which partition should I work, and then they run basically a part of the pipeline. And so if we look at this, let me actually draw this slightly differently so I have a little bit more space here. So we saw there was a whole bunch of stages, and then the last stage was the last operation was the collect stage. So in this scenario that we just looked at, the collect stage, of course, needs to collect data from all the partitions, right? So in principle, let's just draw a green line. Basically everything of this, is sort of executed on an independent partition. So every worker, gets one of these tasks from the scheduler, runs, that thing, and produces in the end an time RDD. And when the scheduler, determines that basically all the time, like all these stages, this is called a stage. if all the stages have completed, and so all the time partitions have been produced, then it actually will run, the collect action to basically do the addition and retrieve information from every partition to actually compute the collect, or actually this is not collect, it was count. Sorry about that. And so one sort of way to think about this is that this is sort of like almost like a MapReduce, correct, where you have the map phase and then you have a sort of a shuffle, and then you run the reduce phase. And the count is almost or similar in that fashion. And in the paper, the way they refer to this is to this dependency. They call it a white dependency, because the action or the transformation is dependent on a number of partitions. And these are called narrow dependencies, because this RDD, to make that RDD, is only dependent on one other, only dependent on the parent partition, only one parent partition to actually be able to compute it. And so in general, you would prefer a computation that can have narrow dependencies because they can just run locally without any communication. But for a white dependency, you might have to collect partitions from the parent, or you may have to collect partitions from the parent RDD from all the machines.
Professor.
Yeah.
I had a question. So in the paper, it says narrow dependencies where each partition of the parent RDD is used by at most one partition of the child RDD.
Yeah.
But it doesn't say anything about the contra, like the reverse, like it doesn't say like a child partition needs to use at most one parent
that's correct, because then
partition,
in
and then
if a child uses multiple parent partitions, then it's a white dependency.
If a parent, sorry,
if the child needs the partitions of, if the partitions for multiple parent partitions, then it's a white dependency. So for example, in the count case, correct, you have time partitions,
right,
and the count operation is going to collect data from all of them.
Right.
And so if count were an RDD, it isn't, but like it's just an action. Yeah. But even were an RDD, then basically that would require interaction with all the parents.
What I'm saying is I think it says the opposite, right? I think this might, like, I mean, I was actually confused like with the paper on this on the specific issue, but like it says like each partition of the parent RDD is used by at most one partition of the child, but it doesn't say one partition of the child uses at most.
Okay, I'm not 100% sure, exactly why you're confused about this. So let me can we postpone this and come back to it in the end?
Sure.
I think that the key thing to observe is that basically two types of dependency: white ones and narrow ones. And white ones basically, basically involve communication, because they have to talk to the collect the information from the data from the parent partitions. Okay.
Thanks.
Actually, I have a question on interface.
Yes.
In like the previous like 1 or 2 slides, what happens if you don't call errors.persist?
If you do not, then the second computation, like this computation, would recompute errors from the beginning. So if you run this workload, this Spark computation, it would recompute errors from the starting file.
Got it. Thank you.
So I actually have a question about this point. So for the partitions that we don't call persist on, in the MapReduce case, we basically stored them in intermediate files, but we nonetheless stored them in a local file system, let's say in the case of MapReduce. Do we actually store intermediate files here that we don't persist in some persistent storage, or we just keep the whole flow in memory throughout the whole?
By default, the whole flow is in memory, except you can provide to, there's one exception that we'll talk about a little bit more in detail in a second, hopefully, which is, you see this persist here. This persist can take another flag, I think it's called reliable. And then that set is actually stored in HDFS. And basically, they call this a checkpoint.
I see. Thank you.
I have a quick question about the partitioning that with partitioning the RDDs initially, is it initially HDFS who partitions them for each worker to operate on, or is Spark handling all of it?
So this lines RDFS, the partition is defined basically by the files that are actually in HDFS.
Okay.
You can repartition, and we'll see in a second that actually might be advantageous to do so. For example, using this hash partition trick, and you can define also your own partitioner. There's a partitioner object or abstraction that you can supply.
Okay, so it's already handled by HDFS, but if you want to do it again through Spark, then you can.
Yep. And in some sense, of course, these files are also created
Yep.
by this file is presumably either created by some logging system that sits on the side and just produces different partitions, or you can reshuffle if you want to.
Makes sense. Thank you.
Okay. So let me. So that's the execution model, and I want to talk a little bit about fault tolerance. And so let's go back to this. So this is sort of fault tolerance, and the thing that we worry about in fault tolerance is that maybe one of these workers, might crash, right? And the worker is computing on some partition, and so we need to re-execute that. And basically this plan is sort of the same as in MapReduce, right? Where if a worker crashes, we need to, in MapReduce, the map task need to be re-executed, and perhaps maybe a reduced task has to be re-executed. Now, and here the tasks are slightly more complicated because they're basically like these stages. And so it means that if one worker fails, we may have to recompute the stage. So let's talk a little bit more about that. So that's sort of this perspective from fault tolerance, right? That's what we're trying to achieve. This is really different than like the fault tolerance that you implemented in lab 2 and 3, where Paxos and stable storage and all that kind of stuff. And here, really, what we're worried about is a crash of a worker. The worker loses its memory, lost memory, and that means it lost its partition. And the later parts of the computation are probably dependent on that partition, and so we need to reread or recompute this partition. And so the solution is like exactly like in MapReduce. Basically the scheduler notices at some point that doesn't get an answer, and then reruns the stage for that partition. And and what is the cool part? Like exactly as in MapReduce, if you look at all these transformations that are sitting here in the API, all these transformations are functional. And so they basically take one input, they take an RDD as an input, they produce another RDD as output, and just completely deterministic. And so, like with MapReduce, the maps and the reduce were functional operations. If you restart a stage or a sequence of transformations from the same input, then you'll produce the same output. And so you recreate, the same partition. Recreates partitions facially. Okay.
Sorry, is this why they're immutable?
There's also the reason I think they're ideally immutable, yes. Okay, there's one tricky case though, which I want to talk about. So this, the fault tolerance basically for the narrow case is the same as sort of as we saw before in MapReduce, but you know the tricky case is actually the white dependencies. So let's say we have some transformations, and one of these transformations is dependent on a this is like sort of here we have one worker, we have another worker, we have another worker, and one of these stages is actually dependent on a number of parent partitions. So let's say whatever, maybe this is a join, or we'll see later other operations where we are actually collecting information for lots of partitions and create a new RDD from that. And from that RDD, that might be used again by a map or whatever. Keep it going. And so now let's say we're a worker and we crash here, right? And we need to reconstruct this RDD. And we sort of follow. That means that we have to also recompute this RDD. To recompute this RDD on this worker, that means we also need the partitions on the other workers. And so the reconstruction, the re-execution of a computation on a particular worker or a particular partition may actually result that actually these ones also need to be recomputed. Now, of course, you can do this partially in parallel. You can just ask, please, start, recompute this guy, recompute that guy, and produce then the final RDD again. But certainly, a failure of one worker might result in the recomputation of many partitions, and that's sort of slightly, and so that could be slightly costly. And so the solution is that as a programmer, you can actually checkpoint or persist RDDs on stable storage. And so you might decide, for example, if this is an RDD that you don't want to recompute in the case of a failure because it requires recomputing all the different partitions, you may want to checkpoint this RDD. And then this stage when this computation needs to be re-executed, then we can actually read the result of the partitions from the checkpoint instead of actually having to recompute them from scratch. And so this is why Spark supports checkpoints, and that is sort of their fault tolerance story for white dependencies. Any questions about this?
I had one question.
Yeah, go ahead.
So there was, so you can persist, right? Just in general, but they also mentioned the reliable flag.
Mm-hmm.
So I was wondering, like, what's the difference between just persisting and using a reliable flag?
Persist just means you're going to keep that RDD in memory, and you're not going to throw it away, so that you can reuse it in later computations. And it's just in memory. The checkpoint or the reliability flag basically means you actually write a copy of the whole RDD to HDFS. And HDFS is a persistent or a stable storage file system. Okay.
Is there a way to tell Spark to unpersist something? Because otherwise, like for example, if you persist an RDD, and you do a lot of computations, but like those later computations never use the RDD, you might just have it sticking around in memory forever.
Yeah, so I presume you can. There's a general strategy that Spark uses. They talk a little bit about this, is that if there's really no space anymore, they might spill some RDDs to HDFS or remove them. The paper's slightly vague on exactly what their plan for that is.
Thank you.
Of course, when the computation ends and as a user you log out or you stop your driver, then I think those RDDs are definitely gone from memory. Okay. Okay, so that is almost the story of Spark. We've seen what an RDD is. We've seen how sort of the execution works, and we've seen how the fault tolerance plan works. The thing that I really want to talk about is another example to really show off where Spark shines, and that is an iterative example. So in computation that has an iterative structure. And the particular one I want to talk about is PageRank. I assume that most of you are familiar with PageRank in some form. Basically, it's a plan to an algorithm to give weight or importance to web pages. And it's dependent on the number of links that point to a particular web page. So for example, if you have a web page U1, it may point to itself. You have maybe a web page U3, which I'll use an example, and a web page U2. U2 has a link, to itself and to U3, and maybe U3 has a link to U1. And basically, PageRank is an algorithm that based on these connectivities computes the importance of a web page. And PageRank was sort of the early one of the algorithms that really drove the Google search machine, in the sense that if you had a search result, the way you rank search result is that if the search result appears on a more important web page, that result gets promoted to higher in the list. And that was one of the reasons that in the early days of Google, the Google search machine actually produced better search results, where the more important information actually, or the more important web pages were at top. And so the paper talks about, shows off the an implementation of PageRank in Spark. So here's the implementation of the Spark implementation of PageRank. And as before, this is just a description. So we look at the individual lines. These are just the sort of the recipe to actually how to compute PageRank, and only when, in this particular case, if you do say ranks collect at the very end, then actually the computation would run on the cluster of machines, and using sort of the execution pattern that we have seen so far. And so I want to walk through this example in a little bit more detail. To get a sense, get a better sense why Spark sort of shines in the iterative case. So there are two RDDs here, and also going to talk about some optimizations that are cool in Spark. One is this links RDDs, and links is basically represents the connection of the graphs, and so basically it probably has a line. I'm just going to write it like that. It has a line per URL. So here U1, and it has two outgoing links, U1, U2, U3. Yeah. Actually, I missed one link here. And then there's a U2 entry for U2, which has an outgoing link to U2 and U3. And there is an entry, U3 going to U1. So this is basically a description, if you will, of the World Wide Web. And so, of course, in my tiny little example, I have 3 web pages. But if we're running this at the scale of Google, you would have 1 billion web pages, correct? And so this file is gigantic and is partitioned in partitions. So that's links. And then ranks is a sort of similar file that contains the current ranks for these web pages. And so you can think about this as, U1, comma, its rank. And let's assume that the ranks are initialized at 1.0. Then, here's 1.0. And, U2, 1.0, U3, 1.0. And we see actually that the links RDDs is actually persistent in memory. That's presumably like in the same way as the error file that we saw before, or the error RDD. And then ranks, is initialized, to something, and then basically there's this sort of a description of a number of iterations to produce a new ranks RDD. And then you can see a little bit, how this actually plays out. And one of the things to notice is that links gets reused in every iteration. And links actually gets joined with ranks. What does it mean to actually do this join up, this operation? This operation basically creates an RDD, right? And how does that RDD look like? Well, that RDD is going to look like U1, and then the join of the ranks and the links file. So it's going to be U1, U2, because those are or U3, the outgoing links plus the rank for U1, which I'm just going to go write as rank 1. And that's sort of the RDD that's being produced here. And so same thing for, whatever U2, and the one for U3 is whatever U1 and, are free, rank for free. Basically, it just merges the two, literally joins the two files based on key. Okay. And then, it runs a computation of flat map on this, and that flat map itself internally has a map over links. And so basically, it's going to run over, make this clear, it's going to run over these lists and basically partition or divide up the rank, to the outgoing URLs. And so it will, create tuples of the form, let me write this in green then, U1, R1 divided by 2, and U1 or U1 free over the outgoing link. So it gave 1 to U1, 1 to U3, here's U3, R1 divided over 2. Etc. So it creates tuples of this kind of form. So basically, it computes the weight, it divides the rank across the outgoing edges and gives the values of these ranks to the outgoing edges. So the outgoing edges. So we're going to get a big RDD that has this form, and that's produced basically. That is the contributions RDD. Then there's a final step. In the I think at first it was reduced by key, so basically grabs all the U1s together and then sums them up. So basically, this will result is that all the weights or the fractional weights that U1 is going to receive are being added up. So U1 of course is going to receive weights from itself. This one is going to be weight from U3, and so we'll sum them up. It's going to be R1. Divided by 2 and R3 divided by 1, and that is basically the sum that's being computed. And so that produces a list of sums, and then actually they're added up and computed into a final value. And that produces the new ranks RDD, which has this same shape as the one that we saw before, namely this shape. For every web page, there is a number. Does that make sense? And so it's interesting to, that's sort of the description. So first of all, you can see that the description of PageRank is quite precise. And this is one of the examples. This is like if you had to run this in a MapReduce style, then that would mean at every iteration, of this loop, at the end of the iteration, you would store the results in the file system, and then you reread, the iteration from the result for the next iteration. And in this Spark system, you just every iteration you just run straight out of memory, leaves the results in memory so that the next iteration can pick it up right there. And furthermore, this links file is shared among all the iterations. Okay, so to get a little bit more sense of like, why this is also very cool, the way to look at it is to actually look at the lineage graph for this particular computation. So let's look at the lineage graph for, so here's the lineage graph for for PageRank. And so the couple of things I want to point out. But first of all, so the lineage graph is like dynamic almost. Oops. It just keeps growing, with the number of iterations. And so as the scheduler, basically computes and does new stages, then it keeps going. And we can see what the stages are going to be, correct? Because sort of, every iteration of a loop is one stage, and will basically append parts, transformations to the lineage graph. So we see here's the input file, here's the links, and as we saw, like links is actually created once, then persisted in memory, not on disk, persisted in memory, and is being reused many times. Like in every loop iteration, basically ranks is being reused. And so again, compared to MapReduce, if you have to write this in the MapReduce style, you don't get that reuse. And so that's of course going to like tremendously improve performance, because links, as we said before, is like this gigantic file that basically corresponds to one line for every web page in the universe. Another interesting thing to observe here is that we see white dependencies here. Right? This is a white dependency, or could be a white dependency. We'll be a little bit more sophisticated about this in a second, because basically these contributions, when we contribute the intermediate result, it is a join across ranks and links. And so it needs the partitions from links, and it needs partitions from ranks to basically compute a partition for the contrib RDD, sorry. And so that might require, some network communication. But it turns out they have sort of a clever optimization. And this is in response to an earlier question about like partitioning. You can specify that you want to partition an RDD using a hash partition. And what does that mean? Is that the links and ranks file, these two RDDs, are going to be partitioned in the same way. They're going to actually partition by key or by the hash of a key. So if we go look back, at our previous picture, the keys for ranks, are U1, U2, U3. The keys for the links, the keys for ranks are U1, U2, 3. The keys for links are also U1, U2, U3. And basically, the clever optimization, and this is a standard optimization from the database literature, is that if you partition links and ranks by key, then this one is going to have U1 on one machine. Now maybe this has U2 on one machine. Then ranks is going to have the same thing. It's going to have U1 on one machine. And in fact, it's going to have U1 on the same machine as the links one, and same for U2 and U3. So even though this join is conceptually white dependency, it can be executed like a narrow dependency, because basically to compute the join of these two for the U1, for the first partition for P1, you only have to look at the partition P1 of links and P1 of ranks, because the keys are hashed in the same way to the same machine. And so the scheduler or the programmer can actually specify these hash partitions. The scheduler sees, the join actually uses these hash partitions. The hash partitions that are the same, and therefore I actually don't have to do this white dependency. I don't have to do sort of a complete barrier as in MapReduce, but I can just treat this as a narrow dependency. So that's pretty cool. then, again, if a machine fails, correct? We talked a little bit about this earlier. That might be painful because you may have to re-execute many loops or many iterations. And so, if you would probably write this for real, then the programmer will probably say, like, maybe every 10 iterations, basically checkpoint. So that you don't have to recompute the computation all the way from the beginning.
Oh, so we don't actually recompute links or anything each time, right? Like we don't persist it, sorry.
We don't persist it. No, not at all.
Okay.
The only thing that was persisted was only once was links, correct? This was the only thing that had a persist call.
Oh, we do persist it.
Links we do,
Okay.
but not the intermediate RDDs. Because they're basically new RDDs every time. Like ranks 1 is a new RDD, ranks 2 is a new RDD, right? But you may want to persist them, occasionally and store them in HDFS so that if you have a failure, you don't have to go back to loop iteration 0 to recompute everything. Okay, does this make sense?
I'm sorry, the different contribs, can they be computed in parallel?
On different partitions, yes.
Because there's like this line that goes vertically down.
If vertically down, it's pipelined, correct? And then there's two types of parallelism. There's stage parallelism, and there is sort of parallelism between different partitions. And we can think about this thing, like this whole thing, like running many, many times on different partitions.
So in this case, the collect at the very end will be the only place where we have a wide.
Yeah, exactly. The collect is the only one that's gonna, whatever year we have more petitions, correct? I'm making a mess of this picture, but that is has to get them from everyone. Okay, I hope that everyone sort of sees this is actually pretty cool, correct? There's by expressing these computations as sort of a lineage graph or a data flow computation, the scheduler has a bit of room for optimizations, like these exploding hash partitions. We get a lot of parallelism. We get also a lot of reuse. Where you can keep the results of one RDD in memory so that we can reuse it for the next iteration. And you can sort of see that these techniques combined, are going to give you significant performance optimization. And allows you to express more powerful or more instant computations. So maybe with that, I'll summarize this lecture. So a couple things. So RDDs are made by functional transformations. They're grouped together in sort of in a lineage graph, which you can think about as a data flow graph. And this gives this allows reuse. It also allows some clever optimizations by the scheduler. And basically allows also more gives more expressiveness. Yes, then MapReduce by itself, and which results basically in good performance because like a lot of the data just stays in memory. And so if you're excited about this, you can try it out. You just download, Spark, play around and write some programs, or go to databricks.com and create an account, and then you can run Spark computations on their clusters. So if you're excited about this and want to try it out, it's pretty easy to do so. Like unlike Farm, you can just not play with But this actually, you can actually go out and try out. Okay, with that, I want to stop for today. And the people that want to hang around and ask more questions, please feel free to do so. The other thing I want to remind people of is that the deadline for 4B is a little bit away, but I just want to remind people that 4B is pretty tricky, requires a bit of design, so don't start too late. And with that, I'll see you on Tuesday. And again, if there are any questions, I'm happy to answer them.
Thank you.
I had a question about the checkpoints. I think in the paper they mentioned automatic checkpoints using data about how long each computation took. And I wasn't really sure what they mean by this. What are they going to be optimizing for?
The whole checkpoints is correct. There's an optimization between taking checkpoint is expensive, and so that takes time. But re-execution, if there's a machine failure, also takes a lot of time. And so, for example, if you take never a checkpoint, then you basically have to re-execute the computation from the beginning, right? But if you take periodically checkpoints, you don't have to repeat the computation that you did before the checkpoint, but taking the checkpoint takes time. So if you take very frequent checkpoints, you don't have to recompute a lot, but you spend all your time taking checkpoints. And so there's sort of an optimization problem here. You want to take the checkpoints in some regular interval that you're willing to take to recompute.
Okay, so maybe like compute checkpoints only for very large computations.
Yeah, or like for example, in the case of PageRank, maybe do it every 10 iterations.
Thank you.
It depends, of course, of the size of the checkpoint, right? If the size of the checkpoint is small, you can checkpoint more frequently. But in the case of this PageRank, that checkpoint is going to be pretty big. There's going to be a line or a record, per web page.
That makes sense. Thank you.
You're welcome.
I have a question about the driver. Does the application does the driver is the driver on the client side or is
yes?
Okay.
Yeah, the driver's on the client side.
If it crashes, we lose like the whole graph, and that's fine because that's like the application, right?
Yeah, I don't exactly know what happens because the scheduler has it too, and the scheduler is fault tolerant. So I don't know exactly what happens. Maybe you can reconnect. I don't know.
I had a question about the Y dependency optimization. You mentioned that they do like the hash partitioning. How does that work?
Okay, I can say a little bit more. So this is not hash partitioning is not something that they invented. This is actually something that is a standard database partitioning scheme. And it is cool because if you need to compute a join, you don't have to do a lot of communication. So let me I can maybe start a new slide because it's a little bit hard to read. So hash partitioning. So if you have two data sets, here's data set 1, here's data set 2, they have keys, right? Like key 1, key 2. So they have the same set of keys. Then what you do by hash partitioning, you partition the data set in a number of partitions. So boom, boom, boom. And you hash the key. So you hash K1, you hash K2, and that actually determines the partition it ends up in. And so all the keys that actually have the same hash will end up in the same place. So like this is machine 1, this is machine 2, this is machine 3. So you take, whatever, you hash K1, that goes in here. You hash, whatever K2, maybe somewhere else in the file, who knows where it is, and you hash it to that partition. You do the same thing here for the other data sets. So this is data set 1. This is data set 2. Like links and ranks. And what will happen is that all the records in this data set that have the same keys as records in the other data set, those keys or those records will end up in the same machine, right? So here you're going to partition this guy, and basically K1 will end up here too, on the same machine. Correct, and same for the other L keys, because you basically use the same hash function and you have the same set of keys. And so this allows you to take a data set, partition them both in the same way using this hashing trick. And this is cool because now if you need to do a join over these two data sets, like if you need to do a join over these two data sets, then basically you can just join the partitions. And you don't have to communicate, each of these machines doesn't have to communicate with any other machine, because it knows it has all the keys that that the other data set has, and they're all on the same machine.
Gotcha. So basically, it's just trying to not sort, but like bucket the different data sets in the same machine so that it doesn't have to communicate.
Yeah, exactly. So this is just a bucketing trick.
Okay, great. Thank you so much.
You're welcome.
So this means that the hash function has to make sure that there are no links that would have to be like used for the computation on another machine, right? Like for instance.
Yeah, well, since they use the same hash function and they have the same keys, that will happen.
I had a question. I actually wanted to come back to the question I asked before.
Yeah. Good.
So let me open up.
Yeah, let me also open the paper again. Well, if there are any other people that have questions, because maybe this will take a little bit of time.
Yeah, actually, I had a quick question on the fault tolerance of farm.
Yeah.
So,
good. Yeah.
So just to clarify what happens. So if a failure occurs before the decision point, then the entire thing is aborted. But if it occurs after the decision point, then after the failed computers come back up, they have to re-ask the coordinator for whether or not they should commit.
They don't really re-ask, correct? Like what happens is after failure, there's a recovery process runs. And the recovery process looks basically, all the logs are drained, and then the recovery process looks at the state of the system, and based on the state of the system, it decides what to do with the transaction. Either it aborts it or commits it. And the key aspect here in this protocol is to ensure that at the point when the transaction coordinator actually has reported to the application that the transaction succeeded, committed, it has to be the case that there's enough pieces of evidence left around in the system so that during the recovery process, that transaction is definitely committed. And that's sort of the plan. And the reason that there's enough evidence is because there's these log records lying around, there's these commit backup records lying around, and there's this one commit record.
I see. So if something, for example, if a failure occurs on a primary before it gets a commit primary, what happens there?
So that's interesting. So there's enough backup records, correct, to basically decide, that every backup, that every shard actually has committed. And so that's enough information for the recovery process to say, oh yeah, I'm going to run forward with that transaction because it could have committed.
Got it. So it doesn't need the primary in that case. It can use the backups because the backups have the commit.
Exactly.
Got it. Thank you. And what happens if the backup fails?
Well, if one of the backup fails, then presumably that means that the commit record is still there. And then again, that is enough information to decide that actually the transaction needs to commit. And there's enough backups around to actually know what the new value is. Or there's also the log entries, which actually contain. So if a primary is up, it will have a log entry. There will be a commit entry. Plus, there's enough backups to actually finish the transaction.
Thank you.
Wait, sorry to follow up on that. If you said that if the primary failed, then you could use the backups to complete the transaction if there's enough of them. But would you need to elect a new primary?
I think this has all happened during the, basically you can think of the recovery process as a primary. And that just finishes everything off.
Oh, so like whoever does the recovery is the primary?
Yeah, exactly.
Okay, makes sense. Thank you.
I don't think explicitly they, promote a primary. You just like go ahead and do it.
And what is like enough backups?
Well, we have F+1, correct? And so it means that, as long as one is left, we're good. So we can't have more than f+1 failures. We can only have f failures. In this particular drawing, f is 1. So there has to be per shard, one machine left.
Okay, that makes sense. Thank you.
You're welcome. Okay, Philippe, it's just me and you.
Well, unless anyone else has questions, I think.
Let's go.
So it's page. They explain it in page 6.
Yeah, let me look it up.
Right below table 3.
Yep.
So in the paragraph that starts the most interesting question, right? It goes on to define.
We found it both sufficient useful to classify dependencies in 2 types: narrow, where parent partition of the parent ID is used by most one partition of the child ID. Correct. So this is
right.
So let's draw this. Correct. So here we have a parent partition.
Right.
And let's say there's a map. And here we have the child partition. Okay.
Right.
Good. So that's the narrow. This is the narrow case.
Right. But I think like the example I was thinking of is, each parent is used by at most one partition of the child, but the child, right? That doesn't say anything about, like, it says, right? Like, it doesn't necessarily mean it's a one-to-one relationship, right?
Well, because more or less have to, correct? Like, just let me, let's say we have a wide one, correct? So then here we have parent partition 1. Here we have, maybe it has n of them, correct? Here was 2, and here's n. And in the white one, the child is
right. What I was saying is, I think, based on the definition given in the paper, this could be a narrow partition. And in fact, I mean, like, if you look at like a join with inputs co-partition, like you have
the hash partition that actually the wide one turns into a narrow one.
Right. But you still have like a partition, a child partition getting being computed from several
parent partition,
parent partitions, right?
I think they explicitly mentioned that, right? I think that's the only example.
Yeah, but like,
I think there's a typo in that sentence, correct?
I mean, I'm not sure if it's, I'm not sure, like, if it's what they meant to, like, write or
what we know, we conclude this is the 2 cases. Like, I got it here. I guess, and there are no other cases.
Well,
and so like, we can go for every operation, correct? And then we can see whether it's a narrow or a wide one.
Right. But
and the ones that are, and it's the job of the programmer that defines these operations to actually indicate whether it's a wide partition or a narrow, or a wide dependency or a narrow dependency, correct? That's what the figure or table 3 is about.
Like, what I'm saying is, like, usually like the way, like, I saw it through the paper, like your example on the right would be would be a narrow dependency, unless, right, like, you have several childs and the parent partitions are like
so in general, right. It is the case, of course, like, if there's another child partition here, so maybe this is why we're trying to get it. So let's separate the real picture I should draw is this. So here's another child partition, and basically operations, the transformations are
exactly, and that's narrow for sure, right? Like,
this on the right side, this is wide.
Oh, sorry, that's wide. Yeah, that's what I meant. That for sure is wide.
And the other one is wide. The one I drew is also wide, I believe. Like, for example, if you do a join, if you do an action like collect at the very end. Yeah, it's a wide dependency.
Yeah. Okay.
Because it doesn't
I-
say that it doesn't say it has to come from different RDDs. It just says like it has to come from different partitions. And so this is narrow. So I think narrow is only the case where there's one-to-one.
Okay.
Narrow is like narrow means no communication.
Right. Okay. Yeah. Yeah, I think the case where I was like confused was like the many to one, like I think based on the definition of the of the paper, like the many to one relation is still narrow.
No, I don't I think they mean it to be.
I mean, yeah. But like strictly, like if you read, like, yeah, I think maybe like an implementation, you'll see like, yeah, what are you saying, right? Like it's wide. I was just like, I think if you read like the
yeah, you could be confusing.
paper textually, yeah, like you can get confused on like the many to one relation, but the one to many is clearly wide, yeah. But yeah, okay, sounds good.
Okay.
Yeah, that also
Well,
makes like I think the paper easier to understand in general.
Okay, great.
Good. Okay.
Yeah, this was an
Thanks,
easier to
Professor.
understand paper than the farm. And
Oh yeah. Yeah, for sure.
yeah, I think I think those were probably the most two heavy-duty papers that will see this term.
Okay, nice.
Farm and
Yeah.
Farm and Spanner. I think the remaining ones
Yeah.
are a little bit more, more. I wouldn't say straightforward, but perhaps fewer moving pieces.
Nice. Okay, awesome. Thanks, Professor.
Can I ask one last question? I just realized that I have. It was about the computation. You can parallelize it if it's on different partitions, but if it's also, you said if it's in.
Yeah, this is the stages, correct? They're sort of what is it, like streaming parallelism, if you will, or pipeline parallelism. Let me see if I can find a picture that's one of them. Boom, boom, boom. I gotta find a lineage graph. No. Oh, here's what a lineage graph. Great. Now maybe here's a picture that we can modify. Do you see it?
Yes.
Okay. So basically, this is the lineage graph, and here was the collect. And so this is like one stage, right? And the scheduler runs one of these stages on each worker for each partition, right? So each worker runs a stage on a partition. So basically, all these partitions or all these stages run in parallel on different workers. Then within a stage, there's also parallelism. Because every filter is pipelined. With that, they mean like you read maybe like the first n records, and then you apply the filter operation, and then that produces whatever a few m records, and then the next filter process those m records. But while it's processing those m records, the first filter reads the next n, and produces them, and then passes them on, and then maybe that results in some number of records m again, and it goes on and on. And so basically, all these transformations are pipelined, and so they're almost running concurrently, or they're running not truly concurrently, but they're running in a pipeline fashion.
Oh, I understand. This is the batch thing that they were talking about.
Yeah,
right?
exactly.
Oh, okay.
Yeah, so things are passed in batches, and basically every stage of the pipeline processes batch.
Okay. That makes it super clear. Yeah. Thank you so much. That was an interesting lecture. Thank you.
Okay, you're welcome. Glad you enjoyed it. It's a cool system. Okay.
Sorry, can you hear me now?
Yeah. Oh, I didn't hear. I saw you. I was not wondering whether you just checked out or
Yep,
whether
no
you had
problem.
questions.
Nope. I'm sorry about that. Sorry, I was listening. I realize we'd be going late. I'm going to try to make this question very quick.
That's fine.
I've gotten to use Spark
I've
before.
adjusted my schedule.
Oh, thank you.
Dealing with all this kind of
Thank you
stuff.
so much. So yeah, I really appreciate this lecture. Spark is actually something that I'm going to use in my future job, so I appreciate you teaching this to me. Just
Although
one
I'm probably,
thing.
you know, I'm not sure this lecture will really help you writing Spark programs.
No, I mean, I did it as an intern, really not knowing what I was doing, but like this has helped me get more context with it.
Yeah.
So I guess the quick question with Spark programs that the way that I've understood Spark jobs is how Spark constructs a directed acyclic graph of all the tasks, and
this lineage graph. Yeah.
Yep. And this is what you talked about with the wide partitions and narrow partitions. How like
Yeah.
so
dependencies, because they're called dependencies, not partitions. But
yep. Sorry. Okay. Okay. Sorry. That with RDDs, then I guess like, okay, this is different terminology between the dependencies are like these tasks in the directed acyclic graph of all the tasks, but the RDDs, that like each task in this graph is not represented by this RDD.
Let me actually go back. So maybe this picture is the right.
Yep. And oh gosh, I appreciate you staying here. Please let me know if you have to go.
No, that's fine. I got some more time. Yeah. So
Thank
let's
you.
see. Okay, so this is sort of an RDD, correct?
Yep.
Let me draw another color so that we can agree. This is an RDD. Okay, an RDD has a bunch of partitions. And here's another RDD. Correct?
Okay. Yep.
And the arrows are basically, so like here's the same story. Let me actually finish this picture too on the side. Here's some more partitions. Here's the RDDs, boom, boom, RDD, boom, boom, RDD. And then the transformations basically between RDDs, correct? And so in the arrows, let me pick another color. You know, these arrows, those are transformations.
Got you. And this is like part of the directed acyclic graph of the Spark job. Every single transformation leads to like creating another RDD.
Exactly.
That makes sense. That makes sense.
Okay. And then the only thing is like some of these arrows are white and some of them are narrow. And from the graph, you can't really tell which ones are narrower or which ones are which transformations are sort of narrow transformations and which ones are white transformations.
You're talking about the graph that's the Spark program actually like shows you in there.
Yeah, this lineage graph, you can't tell.
Gotcha. Okay.
And that's the here. So here, if you look at this lineage graph, like this transformation, that transformation, all that transformation, they all look like narrow because it's a single arrow, but it's not really true, right? Like the last one, for example, must be a white one because it will collect information from all the partitions.
Okay, then I guess I was wondering, like, do you have recommendations on resources for things that can show me how Spark figures out how to construct the directed acyclic graph to do all these tasks?
Yeah, look at so it's really the scheduler that does all this.
Right. And yeah, reading the paper, like I was trying to comprehend the paper as best as I could, but it's difficult. But
all these papers are difficult to read. So the scheduler, I think I would go back first to Matthijs' doctoral thesis. I'm sure he has a chapter on the scheduler.
Got you. All right, I'll look at it, and that'll show me just how Spark figures out how to make this graph.